Thanks a lot for the introduction. So in this talk, I'm going to talk about a multi-core system, but as opposed to what we have seen before, this system is not supposed to be used in a high-performance application, but it's meant to be used in very tiny IoT and node devices with constraints of a few milliwatt or a few tens of milliwatt of power consumption. And Mr. Worf is the latest chip we have developed in our group, which is a collaboration between the University of Bologna and ETH Zurich. And this is made in the context of a project which is called PULP, which is started 6 years ago. So first of all, I'm going to introduce the concept of parallel ultra-low power computing. Then I will introduce...
David, can you check if your microphone?
Okay, better now?
Yes.
Okay, then I'm going to explain the architecture and the physical implementation of the Mr. Worf SoC. Then I will explain the next step, which will be the introduction of the new concept of trans-precision computing. And finally, I will provide a brief description of the open source ecosystem enabled by the PULP project, and I will conclude my talk. So basically, what we are targeting in this project is computing for the Internet of Things. The Internet of Things is composed by tiny systems that probe the environment through different kinds of sensors. And there are some of the sensors which are currently used in the Internet of Things, which provide extremely low bandwidth, such as temperature sensor or pressure sensor or inertial units. And the computing related to this kind of sensors is very small. So in most applications, a computing system or a microcontroller is supposed to get data from the sensor and transmit it to the internet through a very small computing platform. When we increase the kind of sensor that we use in this kind of system, we can extract more meaningful data from the environment, such as audio information or video information. But when we extract this kind of information, the requirements of the processing needed by this kind of sensors are much higher, in terms of hundreds of MOPS, mega operation per second, up to GOPS. And for this kind of system and this kind of elaboration, a solution that allows to analyze these algorithms in the very low power consumption is not available. If you take a look at the landscape of microcontrollers, we see that there are very low power microcontrollers that can provide very small performance and higher power microcontroller with smaller energy efficiency. And the common trend is that the performance increases and the energy efficiency decreases. So the goal of the PULP project is to be efficient on a wide range of performance. And the main thing that we want to leverage in this project is to increasing the parallelism of the accelerator in order to get performance increase at high energy efficiency. One of the key elements we leverage in the project is low voltage operation. Basically, by reducing the operating voltage of computing devices, you can increase the energy efficiency due to the quadratic dependencies of the supply voltage with the power consumption. The problem is that when you reduce the supply voltage, also the frequency increases. So in order to operate at a high energy efficiency with a reasonable performance range, the only option is to increase the parallelism of the computing platform. But this comes with several problems. One of the problems is the inherent overhead of parallel systems. So most of the applications are not always parallel, and due to these characteristics, we need to be sure that every processor is completely power gated or clock gating or clock gated during unused phases of computation. And another point is the cost of synchronizations. In several parallel applications, we have a lot of synchronization barriers, and we need to make sure that the overhead of synchronization and of adoption of parallel programming languages such as OpenMP is minimized through efficient hardware implementation. And another point that is linked to the applications, Internet of Things application, is the duty cycling. Many of these applications require to operate in a duty cycled manner, so it's important that edge devices can implement in a very efficient manner deep split mode in order to efficiently duty cycle, and this deep split mode should be state retentive in order to wake up rapidly and with low energy overhead. So the Mr. Worf SoC is an Internet of Things processor, which is composed of a standard microcontroller, which is described in the SoC part. Basically, this microcontroller is built around a tiny processor, which has the same computing capability of Cortex M0 Plus, more or less. And this processor operates on a multi-bucket L2 memory and on a I/O subsystem which is connected to a lot of peripherals. And the set of peripherals available in Mr. Worf are the ones typical of IoT devices, such as SPI, camera interface, E2S to connect to microphone. But there are also other peripherals, such as an hyper-RAM interface, which allows to connect to a larger memory, which is in the range of a few megabytes, which is needed to operate highly complex data analytics algorithms such as convolutional neural networks. The main feature of Mr. Worf is the capability to offload highly computer-intensive tasks on a parallel clusters of processors. The processors composing the cluster, which is composed by 8 processors, are more powerful processors, which include DSP extension for energy efficient digital signal processing. I will explain later on. The processor can communicate to a multi-bucket shared data memory through a logarithmic interconnect described here. And the goal of this interconnect, which is a single cycle latest interconnect, is to allow every processor to access its memory bank in one cycle. In addition, the interconnect allows to implement a word-level interleaving scheme in order to spread the access to the memory banks in an even manner. And this allows very flexible exchange of data among the processor, enabling data parallel programming models such as OpenMP or OpenCL on the cluster. Another key element of the cluster is the shared instruction cache. Due to this kind of instruction cache, it is possible to efficiently share the code, which is typically executed in a single instruction multi-dot data application, but without forcing the cores to operate in a lockstep mode, such as in GPUs. This allows to achieve the code density because the same code is stored in a common memory which can be accessed by all processors and allows to implement both SIMD program and MIMD program. Another feature of the processor is the shared floating point unit, which enable the IoT end node to operate on floating point operations, which are required where highly dynamic range operations are needed. So these slides describe the physical implementation of the SoC. In the SoC, we have an L2 memory, which is on the left side of the SoC, which is 512 kilobyte, plus 64 kilobyte of L1 memory. And as highlighted before, it includes a voltage regulator that enables to sweep the supply voltage of the cluster and the SoC part from 0.8 to 1.1 to adjust the operating frequency and voltage with the requirements of an applications. And it allows to implement a full state retentive deep sleep mode in 100 of microwatts. So all of the 512 kilobyte of L2 memory can be put in deep sleep mode, and depending on the requirements of the application, it can be also less to save power. One of the key elements of the processor is the RISC processor, which is based on the RISC-V ISA. So RISC is a 4 pipeline stages processor optimized for energy efficiency. It is 40 kilogate with 30 logic levels, and it features a core math per megahertz of 3.19. It includes several DSP extensions which are optimized for near sensor data analytics, and it supports the RISC-V privilege mode to be sure that it can, one user can run in the user or machine mode. And it has also physical memory protection to deal with the protection of memory elements during execution in different modes. The extensions of the PULP processor extend basically the baseline ISA of the RISC-V processor, and are divided in V1 extension and V2 extensions. So the XPULP V1 extensions are extensions that can be, let's say, used in an efficient manner by the compiler. And these extensions include hardware loops, post-modified load and store increment, and Mach extension. The second kind of extension are a kind of extension that can be used efficiently, let's say only if we modified the code and we explicitly instantiate intrinsics or built-in function in the code. And these kind of extensions are very effectively used when we deal with 16-bit or 8-bit data. So using these extensions, it is possible to operate 4 parallel 8-bit operations or 2 parallel 16-bit operations using the data path of the processor. Just to make an example about the potential of these extensions, I have this an example of addition of a vector, and we can see the full code on the left of the slide. So we see that we have the pointers of the array, which has to be incremented every time, and this is costing 2 instruction, assembly instruction for every array. So by exploiting auto-incrementing load and store operations, it is possible to reduce these instructions, to combine this load and add instruction into one instruction, saving 3 cycles. And another optimization can be used implementing hardware loop, which are used to increment the indexes of the loop. By exploiting this type of extension, we can move to 5 cycles per output. And assuming that we are using char here, so we are using 8-bit operation, we can further reduce the execution to 1.25 cycle per output, exploiting the SIMD load and store and the SIMD add extension of the processor. So we benchmarked the processor using an extensive set of applications, and what we can see is that moving from zero risky, which is the processor on the SoC part of the chip, to risky, which is the more optimized processor, we can gain up to 1.8x. Exploiting the general purpose extension of the processor, so the extensions that can be run on general purpose code, we can further improve the performance by 4 times. And when exploiting the SIMD capabilities of the processor operating on 8-bit data, this leads to a disruptive improvement of performance up to 11 times. As mentioned before, one of the key elements for improving energy efficiency of parallel computing devices is an efficient synchronization. So the goal of this efficient synchronization is to reduce the cost of parallelization of parallel programming models such as OpenMP or OpenCL, and put in sleep the processor during the sequential portion of applications. By implementing these functionalities in hardware, with respect to a traditional software approach based on a test and set, for example, on a shared memory, we can improve the latency and energy of barrier operation by 15 times, and the energy and latency of other OpenMP functions such as mutex by 30 to 50%. And this is a very key element to achieve high performance and not to waste energy during the parallelization of applications. So thanks to this very efficient synchronization, we can get energy benefits and speed up also applications where the AMDAL limit is not very high. So for example, here we have example of several applications. We have applications such as matrix multiplication or convolution, which are fully parallel, so they feature an ideal speed up with respect to the number of cores. This means that if I have 1 core, I get 1. If I have 8 cores, I get 8. But in other applications such as FFT, PCA, and SVM, where I have several synchronization barriers, I can get also in these cases almost ideal speed up, wasting in the worst case 1 core of computing capability, with respect, of course, to the AMDAL limit of the application. So with respect to the maximum ideal achievable speed up. So basically, this slide summarizes what we can get in terms of performance from Mr. Worf. It's interesting to note, okay, the increase of performance with respect to the supply voltage due to the due to the better frequency, but also the increase of performance during the execution, due to the execution of application on the parallel computing clusters, and also the performance of the application of floating point operation, which is almost ideal even if the processor hosts only 2 shared floating point units in the cluster. And the same happens for the energy efficiency. When we reduce the supply voltage, we get a better energy efficiency, and we get an improvement of energy efficiency by 12 times when moving from the SoC execution to the cluster execution. So the next step is the introduction of the trans-precision computing concept. So I explained basically this concept in a fixed point, but if we move to a floating point operation, it is possible to tune the accuracy requirement of application during the execution of an application. So basically what we can do is that we can dynamically tune the precision of operation in order to achieve a predefined accuracy target at the end of the application. So what is available in current commercial devices is basically double precision and single precision operations, but in embedded system also 16-bit floating point are available. Only 2 levels of precision are a limited knob, and in this project we are exploring smaller than 32-bit operation. This in order to reduce the energy consumption of its single operation. And this is mainly due to 3 factors. The first factor is the reduced energy which is necessary to execute every application and every operation. The second factor is the vectorization. By vectorizing operation, you can not only reduce the cost of every operation, but also parallelize operation, so reduce the cost at system level. And this is what really matters when you want to reduce the energy. And the third key element is the reduction of bandwidth, which is related to the reduction of the operations. So we have developed for a floating point unit with 4 different formats. The first format is the traditional IEEE 32-bit format. The second format is the binary 16 IEEE. And we developed also a third format, which is now famous, and it is called as brain float. But we actually developed this more than 1 year ago. And the good thing of this format is that it has the same dynamics as the 32-bit format. And this eases a lot the reduction of precision in applications where you want to maintain the same dynamic as the 32-bit format, but you can reduce the precision. And finally, we have an 8-bit format. In order to do automatic tuning of the variables inside a program, you need to have a tool that analyzes these formats. And for these reasons, we developed a tool which takes the input a program written with a traditional format, 32-bit, and going through this iterative process, it reduces the precision of variables and keeping the final result within an error bound. We also evaluated the energy consumptions on a real implementation of the units, considering the system level, so the processor, pipeline, plus memories, plus functional units. And we can see that the idle power is around 62 picojoule. The arithmetic units are almost identical to the floating point units in terms of power consumption. When we reduce the mantissa of the operations, we have energy decreases, but this is not very relevant. But we can see that the real key to reduce the energy consumption per operation is vectorization. Using this vectorization, we can move from almost 100 picojoule per operation to 20 picojoule per operation. So we have integrated these units in a compilation flow that that allows to map the floating point, the small float variables into the compiler and into the binary of our system. And this binary can be used as an input for iterations with the automatic tuning loop, or as an input for the final target system. So we profiled our methodology on several applications, and we can see here 2 different kind of lines. The striped lines are the lines where we can exploit vectorization in application, while the bold lines are the lines where we cannot exploit vectorization. So we see that for several applications, we can efficiently exploit vectorization, and this is good for the application. For other applications, we cannot explicitly, efficiently exploit vectorization. And this is due to partially due to the compiler, which is not efficiently able to extract this kind of vectorization, but also, one solution to this is to improve the compiler or to do manual vectorization. If we look at the energy with respect to the float baseline, we can see that for all the applications where we exploit efficiently vectorization, we have a significant reduction of energy, but for some application we can even increase the energy that we consume for two reasons. So basically, first of all, we cannot exploit vectorization, so we don't gain energy efficiency. Second, during the transformation between different kind of floating point operations, we have a lot of cast operations, which we don't have in a standard 32-bit implementation. So this cast operation implements an overhead and increases the energy consumption of operation. So basically, what we can do to improve this in all kinds of applications is to provide inputs to the optimization tool about the additional cost of cast operations, which is currently not implemented, or we can add also the effect on vectorization of the automatic source loop. And this is an area where we are looking for collaboration from compiler teams. So finally, I will tell a few words about the open source ecosystem of Pulp. So we started this project 6 years ago, and starting from last year, we developed and released open source a lot of processors and IPs. So we have a very tiny processor, Cortex M0-like, more powerful processor like RISC, which is the equivalent of a Cortex M4 more or less, and we have also 64-bit application processor. And on top of this, we have all the IPs required to develop full systems, and we have also a few reference systems. The Pulpissimo and Pulpino platform, which are single core platform. We have an open Pulp version, which is a single cluster, and we have a multi-cluster version and heterogeneous system that can be used to evaluate heterogeneous platforms. We have these systems implemented on FPGAs, where we have an ARM processor, 64-bit ARM processor, offloading tasks, parallel tasks to the parallel machines implemented on FPGA. And on top of that, we have also some accelerators, such as convolution accelerator and the cryptography accelerators. On top of the hardware platform, we have implemented a full layer of software stack, which include the compiler, which is built on GCC 7.2, all the virtualization layer, programming model based on OpenMP or OpenCL and OpenVX, and simulation models and FPGA prototyping platform that allow to early develop applications or runtime or whatever on the system. And all of this is fully open source and available on GitHub. So we have demonstrated our platform in several silicon prototypes, and we have a lot of demonstrators of this. And this allowed to enable collaborations with different companies, a lot of companies and other universities in Europe and in the world. And I have to say that the good thing of this is that if you share your work, you can get a lot of feedbacks from companies, and such as verification IPs support for Verilator, and recently also support for debug, which can improve your platform and create an ecosystem around your work. So, concluding, the whole presentation was around near sensor data analytics applications. So technology scaling is not enough to deal with these requirements, and ultra low power architectures are needed. In order to be flexible, I believe that it is possible to use smaller than 32-bit types, but this has to come with a complete software environment that allows to automatically tune applications to deal with this new paradigm. And finally, the hardware, open source hardware and software approach can be used to boost this ecosystem. Thank you.